Welcome to the panel. I'm Gokhan. I'm with IOSG Ventures. IOSG Ventures is a Web3 native crypto firm based in Asia. We've been investing in this space since 2017, and we are proud that many of these panelists are actually our portfolio company. So today we're going to be talking about some of the primitives in the cryptography space and how they're empowering Ethereum ecosystem overall. Let's make a round of introductions first. Would you like to start?
Awesome. Hey, I'm Ratan. I'm a founding engineer at Succinct. At Succinct, we're building SP1, which is a Rust-based, ZKVM lets you prove any Rust-based computation. Yeah, we're really excited about being here today, chatting more about ZK.
Hello, everyone. It's glad to be here. So I'm Xiaohong Chen, the CTO of Pi². So we do verifiable computing for all programming languages, and we take a semantics-first approach. And I think that brings some unique advantages to the world of ZK, so which I'm happy to elaborate on in the following discussion. Yeah.
Hey, everyone. My name is Steven. I work at RISC as the head of strategy. At RISC, we built the first and arguably fastest ZK virtual machine. Along the way, I think we've had lots of exciting integrations. Everything's from ZK rollups to coprocessors to provable applications. And then powering this, obviously, we've built out Bonsai as well as Boundless, which is our decentralized protocol moving forwards.
Hey, folks. Guy Itzhaki, the first non-ZK person here. I'm the CEO of Fhenix. We're an FHE-based Layer 2 and a coprocessor. For those of you who don't know, fully homomorphic encryption, FHE, enables you to run computation on data while the data is encrypted. I'm super excited to be here.
Hey guys, this is Deli, the second non-ZK person here. We're building Automata. We're trying to verify machines on chain. So with that, we can actually have like multi-provers for rollups. Actually, with that, we're actually running one of the multi-prover AVS on EigenLayer as well. So also today, we're here, I guess, because we're actually running the superchain hosted by Outlayer. We'd love to share also like more insights on what TE can do with all the other tags here. Thanks.
All right. Maybe to begin with, if you could all talk about the primitives that you're working on and what sort of unique use cases does it enable. Maybe we can start from there. Deli.
Yeah, all right. So I will just go straight with TE first. I mean, TE stands for Trusted Execution Environment. I think many people already know like a lot of history about it, so I will be repeating those things. So our focus is actually to make use of its verifiability. Essentially, you are able to verify like your machines that run remotely on cloud or on some bare metals with like smart contracts. So we're actually building a library called DCAP library that verifies some of the TEs like Intel SGX, TTX. Actually, on that front, we are working with both Succinct and RISC on like accelerating the verification of the attestations. Another property that might be interesting is on confidentiality that TE can bring to the table. But the thing is, it has been it's broken in the past before. It's probably going to be broken again. So we are actually not relying on that property. We are aware of the issues here. To actually have more like defense in depth, we're actually working with more TEs so that we can have a community of different nodes of different tags. So to make sure that the compute is actually correct and also intact. Other things, I think one thing might be interesting is like some of the AI workload are nowadays being like put into TEs because it's capable of executing very large models over there. We've seen like Apple is trying that on Apple Cloud, Apple Private Cloud, and also OpenAI has released some like blog posts mentioning about like trust computing in the past. So there are really like interesting development over there.
Yeah, or we're taking a different approach to confidentiality. So the underlying primitive that we're utilizing is a cryptography called fully homomorphic encryption. I'll use the term FHE from now on. FHE has been existent, I'd say, over the last 10 years since it was invented by Craig Gentry, the first article. Many people may have heard about it, but I think a lot of folks here think it's very complex and it's very slow. But it's actually not. There's been a lot of progression on both fronts, both in terms of the performance and in terms of the ability to just use it in a very easy and native way. What we're providing is a solidity-based environment. You can write your code in whatever way you want, and you can just use and decide what you want to encrypt and decrypt. And what's unique about FHE fact that you can actually compute over encrypted data. And I know it sounds a bit of mind-boggling because we were always been taught that when you encrypt something, it's meaningless. You have to decrypt it. if you want to execute it, whether you want to do it in a TEE or outside of it. But uniqueness of FHE is that you can actually compute over that encrypted data. It's significantly faster from the early days. And what we're especially excited is the fact that the future around FHE is quite exciting because hardware is coming. It's speeding FHE even further in that respect. I'll let the other folks talk in a minute, but I just want to make sure that people don't end up with this. It's FHE or TEE or ZK or MPC. My end game, and I think the end game that we all see here, is a mix of all of them, and we can talk about like the use cases in a bit.
Yeah, I'll talk very high level about ZK, and the rest of the folks can add to it. But like principally, I think ZK also tackles a few problems, especially the ones mentioned on the stage. Mainly, I think the majority of the use cases right now revolve around verifiable computes. You can use cryptography to verify that you did computation correctly. And the nice piece here about ZK is that you can basically do this sort of proving on any sort of hardware. You don't require specialized hardware to do this verifiable compute. And there's also some succinctness to the proofs themselves. So that means you can basically prove as much computation as you want and combine all of that into a single succinct proof.
All right. So I would say at Pi Squared, our approach is, I would say, different, but it offers something that compensates, right? So all the existing ZK systems and the primitives. So we are taking a semantics first approach. And the reason we do that is we want to support all programming languages or virtual machines or SAs. And for those who don't know, right, you can think of the semantics of a language as a mathematical definition of the language, right? It defines the behaviors of all the programs in that language, right? So in theory, from it, you can derive all the language tools automatically, including ZK tools. And I think what's very interesting, we're doing at Pi Squared, is that we are taking a two-stage approach to get you from your computation of your program, smart contracts, to the final ZK proofs. And the way we do that is we first generate a mathematical proof using the formal semantics, right? And then we implement a very small program called a mathematical proof checker in whatever ZK system or ZK primitive you like to use, and use that to generate ZK proof. And why we do this in two stages? Well, because there are so many optimizations that are possible if you stay in the domain of mathematics, right? So I can generate a much simpler mathematical proofs by identifying and using the right lemmas and so on. And then I only, I try to extract the best performance I can, and before I get into the ZK, which is very expensive. So, and this approach, first of all, right, is compatible with all the ZK, schemes and backends out there. Actually, a major part of our infrastructure is built on top of RISC-0, and of course many other ZK VMs. So we are compatible with all of them. And second, it enabled optimizations that are just simply not available, in the compilation, in the classic compilers. Yep.
Yeah, I'll kind of wrap up here. So at Succinct, I think our goal is quite simple. We want to prove all of the world's software. What does that actually mean? Well, in the blockchain context, we care a lot about verifiability for a couple of key properties. Censorship resistance is quite important. This is why we think rollups are an important place for ZK to take off. Over the past couple of years, we've seen the rise of ZK rollups, ZK Sync, Scroll, and a couple of others. But I think really the shift that we've seen is it's been too hard to prove that software. Let's make it as easy as possible, and let's actually make solutions that work for people today. And I think ZK is finally in a place where it works today. So some things we're quite excited about are, we recently launched OP Succinct, which lets you take any OP stack rollup and convert it into a full validity proven rollup. I think these kinds of efforts within blockchain are quite important and show the maturity of ZK. And we're quite excited moving forward too about how it's going to expand outside of blockchains. We had a residency earlier this year where there were like a bunch of people, 40 people that were working on applications with ZK. I think identity is quite cool. WorldCoin's really pioneered this approach. I think that's going to continue. So our goal is to prove the world's software. And ZK is one conduit, an effective conduit for that.
So many of the primitives that you guys have been working on, they've been researched and studied in the academia for a while. But then in the blockchain context, they're recently new. And some of them are older, like T networks. I remember seeing them back in 2017. And ZK, maybe the first seed rounds were happening around 2018, 17 even. But I'd love to get an opinion about like what is the latest state and where are we in terms of the applicability of these technologies, and what is there, like what sort of breakthroughs happened in the last couple of years that made it possible maybe. Ratan, would you like to start?
Yeah, definitely. I think for us, the biggest change has been, there have been academic papers on ZK since the 90s. What's really changed is both the hardware that we're running on and the algorithmic improvements, right? So the algorithms have gotten significantly better. That's due to like fantastic research over the past decade. And the hardware has also gotten way better too. And I think this transition is quite interesting in that as you move into large workloads, we're seeing people move away from, academic approaches to ZK. In the limit, this is what the best design of ZK is. Now we're really focused on what is the real world implication of the proving cost of a ZK VM today. Like SP1 is highly performant on rollups today. And I think this kind of real world transition, you're seeing it with other things too. I mean, Automata is doing a great job of this with TEs, right? And I think now is a point in time in which cryptography in general is becoming real. And that's the transition for us that we're seeing as it's no longer, a team of a community of 1,000 cryptographers that are kind of working on this really, academic field. It's now real businesses that are wondering, how can I actually integrate ZK in a powerful way? I think SP1 is the best way to do that today. And I think for us, that's where we really see a lot of opportunity.
So maybe I want to zoom out a bit, right? So talk about blockchain. So I think one challenge, of course, we see in the blockchain is we have like these new emerging languages coming out, and so it's very it takes effort, right, to support for those new languages, and I think recently there's also something that we realized at Pi Squared is that there is a lot of work done on the programming languages and formal semantics area. So we know how to generate proofs for computation for a long time. They're not ZK proofs, classic mathematical proofs, but as I discussed, there are unique advantages come with mathematical proofs. They are much easier, quicker to generate, and it's a very uniform way to reduce arbitrary computation of arbitrary programs to a very specific type of computation, which is checking whether a mathematical proof is correct, right? So it's like simplify the problem as much as we can before we get into ZK. So that's what we call the semantics first approach, and that's what we are trying to, because I think there is going to be a very promising and interesting future if we combine the two, right? So we can combine mathematical proofs coming from the formal semantics world, which gives you universality, right? It really works for all languages natively. And all the amazing progress we've seen on the ZK VMs, TEEs, and FHEs. Actually, right, because we have a very simple problem, right, checking mathematics, we also observe, some interesting primitives that which, if we have time, I'd like to elaborate them further. But yeah, just to wrap up now.
Yeah, as the representative of the newborn here, I'll take the stab on FHE. I mentioned it already. Like FHE has been out there for a couple of years, and it was very complex. It was very slow. It has been constant progression up to a point where it's actually mature for applications today. I'll just throw some examples here because many people, when they think about FHE, they say, okay, you know what? Maybe we can do like confidential transactions, but can FHE actually be used in conjunction with machine learning? And what we're seeing is that if you tailor-made and you pick the right problems, you can actually work around FHE quite fast and a point that's actually even feasible for today. Now, you've asked, like, what are we mostly excited? If I go back to ETH Denver, February, nobody at the Ethereum Foundation was actually talking about FHE. We were the one pushing it with a few others, but it wasn't like a big narrative. I was yesterday at the main event. You already have like multiple talks from the Ethereum Foundation around polymorphic encryption. You start to hear Vitalik talking about applied privacy when they're talking about even obfuscation, which is like even the next level around that. So I do feel that the technology has matured, and now it's about figuring out the applications around that space. Because like we're all very technical, and we want to make sure that the technology fits what everybody does, and we can like beat it to death. But at the end of the day, it's about figuring out where that meets what the problems are. How does encryption, whether that's through a TE or through ZK or through FHE, can actually help mature this industry and can actually help attract the additional 1 million, 2 million, 100 million users on top of what we do today. And for me, we've bet on FHE. I'm sure you're going to hear with Automata of their bet on TEs.
Yeah, I will quickly share a few things because we are almost running out of time there. So there has been a lot of exciting things this year. I think many actually cloud providers double down their investment in like this kind of confidential computing because of AI. They see the huge opportunity there. One of the good side effects is actually we now have more like TE hardwares and services running on cloud and bare metals. There are many different types like Intel, SGX, TDX, AMD, SEV, even AWS have their Nitro enclaves. All these are actually generally available on the cloud. We've seen also GPU instances that can be verified like with all the hardware features, which makes really really powerful. Also, like one of the I think biggest use case for TE in like blockchain or in rollups are actually multi-provers. We've seen like a lot of ZK rollups nowadays. They even have TE engineers in-house to build the provers themselves. We work very closely with Scroll and Linear, but we also see like ZK Sync has a like prover implementation themselves. We're just helping them on like all the verification logic to make sure that their prover can be verified on chain. Also very exciting, I think one of the biggest like TE news in Web2 is actually from Apple. They have this private cloud compute which supports their entire Apple Intelligence infrastructure. So essentially they're making use the TEs on your phone and also TEs on the cloud to establish like secure channels so that you can offload some of your like AI inference to the cloud, which is more powerful than your local devices. So these are really exciting development recently. Also, I'd love to see like more interesting use cases coming up. Like WorkCoin is doing this MPC protocol, which runs in TE-capable GPU, so that they can verify each human individually. So these are really interesting things going on now.
All right.
The reality is that it's no longer a technology challenge. It's really about the applications on top of that. I think we see the maturity both in all fronts here,
Right.
and now we've past this chasm, and it's really about like the use cases and less about the infrastructure.
Right. And we talked about like what these primitives enable on a high level, but maybe it would be better if you guys could provide some concrete examples of use cases where they become very useful. And I think, Deli, maybe you can talk about how we're going to make the AI autonomous.
Yeah. I mean, we've seen like a lot of demand on the getting like more and more powerful devices. So AI is definitely one of them. Nowadays, NVIDIA actually already supported TE on their like H100, H200 GPU. I think a couple like clouds are supporting that as well. We actually use Microsoft Azure as well as Google Cloud. So as of today, you can actually literally run a maybe Llama 405B model in this kind of a setup that you get verifiability immediately. You can know that the model running there is correct. You can know that your input is private because nobody can touch the data. Another interesting use case of like this kind of demanding use case is actually WorkCoin. We actually work with them to help them to solve the scalability issue when it comes to verify human uniqueness. You know that there's like doing this kind of orb scanning for the people's iris code, but they really need the service to actually double check if this is an individual person. So to do that, they actually use an MPC protocol that consists of a couple of GPU instances which are running entirely in TE, so that all these nodes couldn't be colluded with each other, and yet the data there is still secure, and they can provide very scalable services for like even like millions of like human users. So these are the like very good overlaps between all the different tags. Yeah.
Perfect.
Yeah, I'll just give a brief example of some of the things that we're actually at this point looking. One of them is the ability to build on-chain reputation. Today, we look at all users on-chain as flat. They're all with the same level. With the ability of now introducing data encrypted on-chain, we can start calculating and providing some sort of a credit score based on user behavior. And once we can attach that credit score, and maybe that credit score is based on their Web2 credit score, or it's based on how they've been interacting with the blockchain for the last couple of years, that actually now enables us to start feeding it into DeFi application and provide these users better lending rates, because what they can do is just show that they're more credible. And all of that is really non-feasible when everything is public out there. And this is the uniqueness that whether you do it with TEs, MPCs, or FHE, we can actually start seeing this industry maturing into more complex and sophisticated applications.
Yeah, so I think for use cases, especially with regards to ZK, at this point there's like more than I can talk about in one moment. But basically everything from obviously rollups, but we're personally more excited about applications too. Like coprocessors are actually a really interesting architecture because you can do like insane amounts of compute. You're talking millions of gas worth of compute in the ZK VM and then connecting that back to Ethereum. We have teams that are building cross-chain governance, bridging. Also, Hashflow is a really exciting team because they're doing provable exchanges, basically using ZK to provide the verification and validity of the order matching so that something like FTX doesn't happen. So yeah, generally, I think lots of really exciting things. We've seen with the advent of ZK VMs that the use cases of ZK have really exploded beyond rollups. And like truthfully, I think people really are hung up on performance and things like that. But for the vast majority of use cases today, I think the performance is basically there.
Yeah, so very quickly, I think looking beyond ZK and infrastructure, speaking of use cases, the question is, how can we enable any developers to build on top of any blockchain, right? So how can we embrace the very large potential developer base who are not familiar with like Web3 languages, but Web2 languages? How can we bring Web2 developers to write smart contracts in any programming languages they are proficient in? So that is a mission and goals at Pi2 we're doing for that. So that's why we push very hard on this universality. So we want to build make our tools so that they can enable any developer to write smart contracts in any blockchain, in any programming languages they like.
Well, we're running out of time, so I'd like to wrap it up. Thanks a lot, everyone, for joining and listening, and thanks a lot for the great insights. Thanks.
Thank you, everyone.